Hi, till now in greedy technique, I discussed an abstract problem, job sequence with deadline, optimal merging pattern, and Huffman coding. Next, I will discuss minimum spanning tree. First, understand what is spanning tree. Spanning tree is a acyclic subgraph that contains all the vertices. So there should not be any cycle. There should not be any cycle means if there are n vertices, then in spanning tree there will be n minus 1 edges. A spanning tree of an undirected connected graph is its connected acyclic subgraph, or we can say it is a tree that contains all the vertices of the graph. For spanning tree, graphs should be connected and it should be undirected. In directed graph, we cannot find spanning tree and it should be connected. If it is not connected, then we will get different component. And for different component, we can make separate spanning tree. It will be not one spanning tree. So it should be connected and undirected. If graph is the undirected weighted connected graph, means some weight are assigned for every edges, then sum of the weight in the spanning tree is called as total weight and the spanning tree is called as minimum spanning tree. So minimum spanning tree is the spanning tree of the smallest weight, where the weight of the tree is defined as the sum of the weight of all its edges that we consider in the spanning tree. And for one graph, there can be different spanning tree. So which one is the minimum? Finding minimum spanning tree called as minimum spanning tree problem. Let's take an example. Suppose this is a graph. There are 3 vertices and 3 edges. Then in the spanning tree, there can be 2 edges, n minus 1. 3 vertices, so 3 minus 1, 2 edges. Suppose weight are assigned, let it 5, 2, 3. Here it will be 5, 3, 2, 3, 5, 2. So total weight for first spanning tree is 8, for second spanning tree is 5, for third spanning tree is 7. This one is the minimum. So to find minimum spanning tree is called as minimum spanning tree problem. This is a small graph, so create all the spanning tree, find the sum and we find the minimum spanning tree. But if the graph will be big, we cannot create lots of spanning tree and find the total weight. So it will be time consuming. That's why there are two algorithms. One is Prim's algorithm, another is Kruskal algorithm for finding minimum spanning tree. First, I will discuss Prim's algorithm for finding minimum spanning tree. Prim's algorithm operates much like Dijkstra algorithm for finding shortest path. Dijkstra algorithm is a single source shortest path. From one source, we can find shortest path to every vertex. So Prim's algorithm constructs a minimum spanning tree through a sequence of expanding subtree. Initially, there will be one vertex. Start vertex will be given. From that, every time we'll add one edges. So whatever the vertex are adjacent to it, whatever the lowest weight or minimum weight, that we'll choose. And it should not create any cycle. On each iteration, the algorithm expands the current tree in the greedy manner by simply attaching to the nearest smallest weight vertex that is not in that tree. And finally, we will check all vertex are covered, all vertex we included, and number of vertex minus 1 edges are there. So since in each iteration it will just add 1 edges, so there will be n minus 1 iteration. At every time it will just add 1 edges. Let's discuss Prim's algorithm. Input is a graph and output will be spanning tree. The start vertex is given. Let V0 is the start vertex and Vt is the vertex in the spanning tree. So start vertex is given and no edges included. So Et equals to 5. Et is edges in the tree, Vt is vertex in the tree. So one vertex is given and no edges are included. Now for I equals to 1 to number of vertices minus 1. In a tree, number of edges will be number of vertices minus 1. That's why for I equals to 1 to till number of vertices minus 1, find minimum weight edge E closure, that is V closure, U closure among all the edges VU. Now V0 is given. With V0 all the adjacent will check and what is the minimum weight edge that will include. So such that V is in Vt. Vt is the number of vertex in tree. So this B is in Vt and U is in V minus Vt. Means U is in the original graph vertex but not in the spanning tree vertex. So B is in Vt and U is in V but not in Vt. And the weight of the edge should be minimum, then we can include. Vt will be Vt union U closure and Et will be Et union E closure. So we'll add the edge and we'll add the vertex to the tree and we'll return Et. That will be our spanning tree. So initially one vertex will be given. From all the adjacent we'll choose what is the minimum weighted edge and that will include, and every time we'll include one edge, and finally when we'll reach number of vertices -1 we'll stop. Let's analyze this algorithm. If graph is represented by its weighted matrix and the priority queue is implemented as an unordered array, the array is not sorted, then the algorithm run theta of number of vertices square. It will be theta of v. For this for loop, we'll traverse the whole array to find the minimum and we'll delete that minimum. So that will be again theta of v. That's why total it will be theta of v square. If the data stored in a min heap, then finding and delete the minimum will be order of log n, or here we can say order of log v. So order of log of number of vertices. So total running time will be order of number of edges log number of vertices. If a graph is represented by an adjacency list and the priority queue is implemented as a min heap, then running time will be order of number of edges log number of vertices. Let's discuss one example of finding minimum spanning tree using Prim's algorithm. Here root is vertex A, start vertex is given. Now with A, B and H are adjacent, weight are 4 and 8. 4 is the minimum, so we'll include B in the tree. Now with A, B, C and H are adjacent, weight are 8, 11, 8. 8 is minimum and there are two edges having weight 8. We can choose any one. Let me choose B, C. You can also choose A, H. Now with A, B, C, this 8, 11, 2, 4, 7 are the weighted edge which are adjacent. So here 2 is the minimum. We'll include C, I. So next with the subgraph weight 8, 11, 7, 6, 4, 7 are adjacent. Here 4 is the minimum. So we'll add F to the tree. Now with this subgraph, this 2 is the minimum weight that is adjacent. So we'll add F, G. Next this 1 is the minimum. So we'll add G, H. Next from the adjacent 6 is the minimum, but we cannot include this, as if we'll include this it will form a cycle. Next is the 7. If we'll include this, again it will form a cycle, so we cannot include this. Next we'll include this 7. So C, D, add a edge C, D. Now which edge is not included? Just E is not included. D, E weight is 9, then F, E weight is 10. So minimum is 9, will include D, E. Now this is the spanning tree which included all the vertex and number of vertex minus 1 edges. Now what will be total weight? Just add 4 plus 8 plus 7 plus 9 plus 2 plus 4 plus 1 plus 2. So total will be 37. In today's lecture, I discussed Prim's algorithm with the example. In next lecture, I will discuss Kruskal algorithm. If this lecture is helpful for you, please like and subscribe. Thank you.